So we were in the middle of proving the theorem by Kotochka and Thomason, which says that if you have a graph with certain average degree, let me see. Let's write down the theorem here again. So it says that there exists a constant C such that every graph with average degree at least C times T times square root of log T as a KT minor. So give me a moment. Yeah, so we want to prove this, and then we discussed about the possible strategy. How you do it is when we have G, we want to take some minors until you get a very dense graph. Let's say you have H, which satisfies that its minimum degree is bigger than the half of the number of vertices plus certain number S. There, by using that, we want to take x1, x2, and so on in order so that the H, xi is connected. And then those selected vertices, each of them, we want to make sure that there are edges between them. And how do we ensure that is that whenever we take each set, we want to make sure that their neighborhood is large, so that and x2 has also large neighborhood, and x3 also has a large neighborhood. And when we choose x4, we can choose x4 which intersects with the common neighborhood of x1, x2, x3, so that x4 is something somewhat here, and then you put it out. Then this x4 has a neighbor with before, the sets before. For that we prove these two lemma. So one is that we can always find many sets of fixed size which dominate, meaning that which has neighbors in many vertices of the remaining part of the graph. And also we need to make sure that each xi is connected. So which can be done by this lemma. When W is a certain set, and we can always add a few more vertices so that they together induces a connected graph in G. So now we want to prove the theorem. So let's say T is at least 4, and R is the integer which is 10 times T times square root of log T, and K with the 2 square root of log T. And let G be a graph with at least say 8R times G edges. Okay, give me a moment. Yes. So now what we first want to do is we want to take a minor of G, which is a H, which has large minimum degree. So for that we want to use some technique. So one of the technique is that once you have some minor. Let's say you take a certain minor h where, say, average degree of h is largest. So meaning that this is largest among all subgraph of G. Then what you do is, if you take one H, U, and V, if you contract it, then you get another graph H prime, where U and V together forms one vertex. Then if the previous one has an average degree R, then this must have something like, let's say, not R, let's use alpha. Alpha H edges, and here you suddenly have a less than alpha times H minus 1 edges. Meaning that the U and V has at least alpha common edges, common neighbors. Because once you go from here to here, when you contract it, the number of edges that you lose is, these two edges become one edge here. So that's where you lose. On top of this one edge. So we can show that they have many common neighbor. Then what you can do is, here you have two vertices, and if you know that they have many common neighbor, what you can do is you take a U with a minimum degree here, and this, let's say this is H, some graph we get. Then every vertex, by the same logic before, every vertex U here has, not U, V. V here, U and V together has many common neighbors, meaning that V has many neighbors inside of here. So if we take this as our choice of final H here, as before, let's say this was not H prime, then we can guarantee certain minimum degree. With some computation, we can actually show that this part satisfies, the condition that we want. Again, because U and V has so many common neighbors, so that means V has many neighbors inside of this neighborhood of U. So if you take a neighborhood of U and then consider the graph, this H prime induces on here, then maybe have a large minimum degree. So that's what we want to do. So in order to do that, let H1 be a minimal minor. Among all the minor of G, we take the one with, so here I said it wrong, it's not the subgraph, minor H of G. So among all minors of G, we choose the minimal one, satisfying the number of edges in H is at least 8R H1. So average degree is at least 16R. Such a choice exists because G itself satisfies this, right? That was our assumption. So G satisfies this, so there must be a one that's satisfying this. Minimal one, minimal H1 which satisfies this. So such a H1 exists as G itself already satisfies this. And let G be a minimum degree vertex. there are several things we know. We have H1 and then G. Then we know that number of edges in H1 is exactly 8R H1 because we choose the minimal one satisfying this, meaning that if this has more vertex in that, more edges than that, then we can even delete some edges. So let's consider this minimal as minimal among the all minor relation. And minor relation, you can delete the vertices or delete edges. So once you delete one more edge, then that's smaller than H1. So it no longer satisfies this 5.1. So we can assume, we know that it has exactly 8R times H1 edges. So that means this G has a degree at most 16R. Now what you do is you take this H2. Let H2 be H1, the induced graph, which is induced by the neighborhood of G. Then for all vertices W in here, what we know, if we contract it from H1, this does not satisfy this 5.1. So we have number of edges in H1 minus GW is number of edges minus degree of W inside of this H2 minus one more edges in here, which is smaller than 8R times H1 minus 1. So this implies that the degree of W in H2 is at least 8R. Because if you move it here and then move everything else here, then we get this inequality. And from here, what we know is number of edges in H2 is at least 4R times H2 by the degree sum formula. So let f of x be the function r times x times, say, log 2 x over 2r plus 2. This is some strange function, but we will see why we choose this function in this way. The reason why we choose this function in this way is that this is slow growing function, so that we can get some information later. And let h be a minimal minor of H2. So H2 itself is actually a bit shy of, having the property that we want. So we introduce this function, and then we take the h as a minimal minor of H2, satisfying E of h is at least f of size of h, f of the order of h. And let's say h is bigger than, say, 2r. Note that we know give me a moment. H2 Give me a moment. Yeah, there was some computation that I did wrong. Let's try to fix it. So we know that this is M16, so we know H2 has M16R vertices. So let's try to fix this by doing this 4R. Okay, satisfying this condition. So let's take this as a F, and we take H as a minimal minor of H2, satisfying this inequality and this. Then we have to first show that such an H exists. For that, we have to first find that first check that this H2 satisfy this condition. So what's the number of H's in H2? We just show that that's at least 4R times H2. And that's R times H2 times log 4R times size of H2 plus 2, which is size of F of size of H2. Here, why is it? So this is at most 16R. If this is 16R, this is 2 plus 2, which is same as this. But this is at most 16R, so that means, this is at most 4. So we get this inequality. And these two are actually same. Let me write it as the same. So H2 exists. H2 satisfies this condition. So such an H exists. And furthermore, we have this H is actually has more than 4R vertices as any H prime with 4R vertices. Has at most 4R choose 2 H's, which is 4R times 4R minus 1 over 2, so which is smaller than 8R square H's. But the F of 4R is actually exactly 2RS and 4R square. Yes. So any graph with 4R vertices does not satisfy this condition. So H has actually bigger than, more than 4R vertices. So now, and I check that it's so by the minimality of H2, we have number of H's in H2. No, H, sorry. What do we have? We have that number of edges in H is same as this. So which is the ceiling of F of size of H. Because otherwise, I mean, if it's less than that, then it wouldn't satisfy this condition. But if it's strictly bigger than this, we can just delete one edge, then get a smaller H. And moreover, let U be a vertex of H with minimum degree. And let H hat be again we do this one more time. We have H and we take U, which is a minimum degree vertex, and then the graph induced by its neighbor as a H hat. Then this is the graph that we will finally use. H hat has a number of vertices is same as the degree of U, which is at most twice times edge of number of edges of H over the size of H, which is twice times the function f, which is r times log 2 4r over H plus 2 plus 1. So this plus 1 is because of the ceiling. So we have this upper bound. Let's say this is 5.2. Now we want to show that this H hat is as we want. This has the minimum degree, which is half of the number of each vertex plus r minus 3. So, as the minimality of H, and H has more than 4 r vertices. That means once you delete an edge or delete a vertex, then this second condition again holds. So that means the first condition is something that's broken. So it implies that if you delete one vertex from H, then suddenly the remaining number of edges is smaller than f of order of H minus 1. And for any H UV, so this U is actually the minimum degree vertex here. For any H UV in H, we have number of edges in the graph you obtain from H by contracting UV is also smaller than this. So we have that the degree of the vertex V in this V hat is actually bigger than the original number of edges in H minus f of order of H minus 1. Because what's the number of edges here? This is number of edges in H minus 1 minus the degree of V in H hat. This is because V here and any edge here is actually forming a common neighborhood of V and U together. And we know that this is same as this. And what's this? This is smaller than f of size of h minus 1. Because otherwise we would have taken the, this graph instead of h for our minimum choice of h. So from here, you move this and then you move this. No, sorry. I should have said that. So this quantity is this. So you move this to here and then this to here, then you will get this minus 1 actually. So that's what you obtain. So now what we do, we have this on the size of h hat, and we have this. So from that, now we want to compute the minimum degree of h minus half times h hat. So what's the minimum degree of h? Which is first this. So which is r times h hat times log 2 and 4r over size of h plus 2. So which is smaller than or equal to this without taking, shielding. And minus r times size of h minus 1 times log base 2 over 4r h minus 1 plus 2, which comes from here, and say minus 1, and half of this. So which is r log 2 h over 4r plus 2, and so we know that this is smaller than that, but comparing this and this and this and this, half, give me a moment, so you subtract it. Yeah, that is true, and then let's just put this all together, say at most 3. Then now we compute. So what's the second term? If you collect the second term, this r h hat times 2 and r h hat times 2, and then this 1 times 2 and this 2 cancels out. So I forgot to write here as a minus. So those parts cancels out. What's the first part? You have this and this and this. So if you rewrite it, this is same as log 2 4r h minus r h log 2 h minus 1 4r plus log 2, let's say rh h over h minus 1. No, let's not write it this way. Minus r log 2 h over 4r minus 3. So this is same. And if you take this term and this term and this term, except that these 3 terms, then what do we get? do we get? Exactly 0. Then we can actually get the remaining term is r times size of h minus 1 log this negative, and here this flips, so it's h over size of h minus 1, I mean hat, no, not hat, sorry, h, because these are all in terms of h, minus 3. And this is actually strictly bigger than r minus 4, because if you just consider this term, this is x times log x plus 1 over x. So x times log 1 plus 1 over x. And this is actually bigger than 1 minus 1 over x for, I mean, all real number x, at least say 1. So, I mean, we get that from this, what we conclude is that delta hat is let's just put, okay, let's actually put 3.5 so that the yeah, we can conclude that this h hat has a minimum degree, at least half of its number of vertices plus r minus 3. Right, so this part is also okay, as we know that this h has, I mean, at least say 2 vertices, no, 3 vertices, say. Okay, so this proves the claim. Now we have the graph as we wanted. So note that we have this h hat is a minor of G. And moreover, we have taken out the U and G first. G is a neighbor of this, and then here, and we take a further contraction on this H. So we have G. And we have further contraction on this H2 to get H. So after the contraction in the big graph, G is again neighbor of here. And then now we take this H hat. So U and G are outside, which are neighbors, I mean, which are all adjacent to this vertices in H hat as a minor. So now we want to just find case of t minus 2 minor inside H hat. Done this together with the previous vertices G and U, I mean, provides a KT minor. So we will find iteratively find the subgraphs x1 to xt minus 2. Let's identify this vertex set and subgraph with the, I mean, let's identify. Meaning that we will write both of these two as x1 and etc. And we will find say subgraph x1 to xt minus 2 of size and most k plus 2 log k plus 1, such that each xi is connected and hxi dominates all but 2 to the 1 minus k times give me a moment. Yes, are vertices of h hat minus all the previously chosen vertices. And there is h between xi and xj for all I, j different. So suppose we have already found x1 to xj for some j which is m of t minus 3. And let g prime be the remaining parts. So we have x1, x2, x3, then we have the remaining g prime, and there are edges here. And let x be the number of vertices we have already taken out. Then we have a minimum degree of g prime is half of the number of vertices in h prime plus r minus 4, which is, minimum degree of h hat minus x, because x many vertices are taken out, so that the degree of each vertex decreases by almost that much. So by lemma 5.17, so from this lemma, what do we know? We have, so here half times s is, r minus 4 minus x is half times x, s. Then we can conclude that this, s, so this is actually bigger than r minus x minus 3. So let's say that, in here, so this is bigger than half times number of h plus s, where s is r minus x minus 3. Then, this inequality, you can actually check that it holds because of our choice of r. And then x is at most t minus 3 times k times, this times t minus 3. That's upper bound on x. So we can actually show that there are at least r minus x choose k many sets of size k in G prime, which dominates all but at most 2 to the negative k times number of vertices in G prime, which is 2 to the minus k times number of vertices in H hat. But the H hat has size at most, what do we know? h hat is smaller than, say, this h, but h has m most size of h2, so this is m most 16r. So 2 to the, say, 4 minus k times r. So this has size m most 16r, so we know this. So for each ij, for each I between 1 and j, we know that m most 2 to the let's change this to 2 to the 4 minus k. Yeah. I'm sorry for keep changing the numbers a bit, but I will update the lecture note before, I uploaded it. So by induction hypothesis, each of I, for each of I, at most, this many of these k sets fail to send any edges to xi, because this xi dominates all but this many vertices of here. So for this xi, the number of vertices, so for this x2, the number of vertices it does not dominate in here is at most 2 to the 4 minus k times r. So that means even after taking x3 out, it still dominates many vertices except at most 2 to the 4 minus k times r vertices. And if all the k vertices come from here, then it fails to have an edge to x2. As long as you have k vertices and at least one of them is here, then there is an edge between this and here, xi. So at most this many of, so if you choose all the k vertices from the part which is not dominated by x2, then that many of k sets fail to send any edge to xi. However, there are j many choices, and each of them you take 2 to the 4 minus k times r, choose k, many give me a moment. The constant is not too important, but maybe we have to change this too. 4, 10. So this many sets of size k fail to send any edges to x1 of the, x1 to xj. So there are this many sets of size k fail to send any edge to x1. There are this many sets of size k which fail to send any edge to x2, and so on to xj. So then many sets actually fail to send any edges to one of the previous sets. And as j is at most t, and then this part you can actually compute you can find this upper bound easily, and this is at most t times 2 to the 5k minus k square over r over 2 to the k, choose k. And you can actually check that this is smaller than r minus x, choose k. So here we obtain this final inequality. From the fact that the 5k minus k square is smaller than log 2t. So that means this part is, goes away. This relation holds because what's roughly this k? K is log of t. Square root of log of t. So times 4 t. Yeah. So if you plug that in here, then we can actually check this inequality holds. And x is at most t times k plus log 2 k plus 1. So that comes from the previous assumption that each of xi has this many sides. So there are at most j of them, and j is at most t. So we get this inequality, and we can actually make sure that this is at most, say, a times square root of log, a times t times square root of log k. And we can show that this is at most r over 2. Let's say this is something like 6. Some of the constant might be, wrong, as there was some computation error on my previous computation, but up to multiplicative error term, you can actually check that this holds. So what does it mean then? We already showed that there are at least this many sets of size k which dominates many vertices except that many. So this is one requirement of xj plus 1 that we want to choose. We want to choose this satisfying 3 conditions. First, it dominates many vertices here except very small number. This small number is 2 to the 4 minus k times r. 2, we want it to have edges to each of these x1 to xj. 3, we want it to be connected. So the one that satisfies the first one is at least this many sets. But the ones that doesn't satisfy the second condition, having edges to here, the one that doesn't satisfy that is strictly smaller than this. So that means there is at least one set which dominates all but at most this many vertices. At least one of them does not fail to satisfy this, meaning that it has edges to all of them. So hence there is a set of size k in Y of G prime which dominates all but at most 2 to the minus k times G prime, which is at most 2 to the 4 minus k times R vertices. Also, since R minus X is bigger than K, and we can actually check I mean, these holes, lemma 5.18 implies this y is contained in a connected subgraph xj plus 1 in G prime of size and most k plus 2 log to k plus 1. So by repeating this for j equal 0, 1, 2 t minus 3, the subgraph x1 to xt minus 2 can be found. And if we contract each xi, then we get a case of t minus 2 minor, and this together with u and g forms a kt minor as desired. So this finishes the proof. On the other hand, I mean, we can actually show that this is sharp. 1980, Bollobash, Katlin, and Eredish show that the random graph Gn half has its largest Kling minor has size and most one plus little of 1 times n over square root of log to n. Let me check the constant. Is this constant correct? Give me a moment. Yes, I think so. Yeah. So this has an average degree half n, which is, let's say this is t, then which is roughly like 2 times t times square root of log t. So this is kind of best possible up to constant. You cannot hope for a, clique of size much bigger than this. And it's also known that for random graph Gn half, we know that its chromatic number is something like 1 plus 0 of 1, roughly n over 2 log to n. And then we know its Hadwiger number is around 1 plus 0 of 1 n over square root of log to n. And we know that between these two, we know that this Hadwiger number is bigger than the chromatic number. This shows that if you randomly choose one graph, so this chooses all possible graph with all possible labeled graph with the same probability. If you consider two graphs with a different label as a different graph, if it is totally different, then the probability that we get a specific graph is, exactly 2 to the negative n choose 2. So every 2 to the n choose 2 labeled graph are picked uniformly at random from this random graph model, binomial random graph model. So if you choose a graph at random, then with high probability, what it says is that its Hadwiger number is strictly bigger than its chromatic number. So this fact shows that the Hadwiger conjecture holds for almost all graphs, meaning that for n we compute the number of graphs. Say this is actually labeled graph satisfying Hadwiger conjecture number of labeled n vertex graph. Let's say, and we compute the number of all n vertex graph here. Then this goes to 1 as n goes to infinity. So this tends to 1. So this shows that this is Hadwiger conjecture is true for almost all graphs. So, okay, this finishes the proof of this Thomason-Kostochka result. And in the next video, we will move to other topic.